Starting with some definitions of probability. Probability seems like a good one to start with. The chance of something happening. Now, there are different types of probability. Experimental probability, also sometimes called relative frequency, that's the probability which you get based upon data that's being collected. Now, all right, here's an example of that. We tossed 5 coins and it went heads, heads, tails, tails, heads. And we'd say, well, the probability of a head would be 3 out of 5. Of course, we know that's not the probability of tossing a head, but that would be the experimental probability. In reality, we know it's a half. That's what we would call the theoretical probability of tossing a head, 1 in 2. And what should happen is as you repeat it over and over and over again, it should converge towards the theoretical probability. So the experimental probability will approach that theoretical probability the more and more times that you do it. Sample space, all the possible outcomes that there are, as opposed to the event space. That's just the number of ways what we're interested in looking at can occur. Equally likely events, things that have the same chance of happening. Mutually exclusive events. Now, that's when only one possible outcome can occur at any one time. So you might be looking at different events. Something like this. A coin. Well, I can toss a head, I can toss a tail, I can't toss both at the same time. So they are mutually exclusive. There's no overlap, which then brings us to non-mutually exclusive events, ones that could happen at the same time. Now, something like this. A number, if I look at a number, the probability of it being even and a multiple of 3, well, they could happen at the same time. There are numbers that are both even and also a multiple of 3. Okay, notation then. P for probability, obviously, but then in the parentheses, whatever the event that we're interested in studying is. So probability of E happening. Now if I put a bar over the top like that, then it's the complementary event, the probability of E not happening. So then basic probability theory. All probabilities must lie in between 0 and 1. You get an answer outside that range, you've done something wrong. Probability 0 is something that is impossible. It never happens. Then we have probability equaling 1, the other end of the scale, a certain event. It's got to happen. It must happen. If all events are equally likely, then that sample space is going to be uniform. In other words, their probabilities are always going to be the same. This is technically a formula for working out the probability. Not that we usually write the formula down, but all that's really saying is, well, the number of items in the event space, the number of ways it can happen, divided by the number of things in the sample space, the total number of possibilities altogether. The complementary event idea comes in very handy. Probability of something not happening then must be 1 minus the probability of something happening. Different ways of listing sample spaces and listing all the possible outcomes would be one. Of course, go back to perms and coms. The reason we did that one is because sometimes it's just not practical to list them all. There's just too many. And we're not actually interested necessarily in what all the things in the sample space are, but just how many there are. And that's why perms and coms is good, because we can work out how many there are without physically having to list. But listing things is certainly a way of doing it. 2004 HSC, they've got this game, involves rolling 2 dice, but they're not ordinary dice. The sides are actually marked 0, 1, 2, 3, 4 and 5. How we get our score is we roll 2 and then we multiply the 2 numbers together. So I'll just list every possible outcome there. Multiply the 2 numbers together, so red numbers there are the outcome. So if I get a question like that now, I just got to pick it from the list. What's the probability of scoring 0? And there's 1, 2, 3, 4, 5, 6 more up there. So I end up with 11 out of the 36. Probability of scoring 16 or more. Well, 16 or 20 is more than 16, so it's 25. 4 out of 36. Notice how I'm setting it out. I'm in there what I'm interested in looking at. Probability equals 0. Probability, it's at least 16. Well, I use greater than or equal to 16, but Don't just write random numbers on the page and expect people to understand what it is that number represents. Oh, that's 1/9, by the way, 4 and 36. Dot diagram, it's another way of doing it. Roll 2 dice, what's the probability? They total 3, they total 7. What's a dot diagram? That's a dot diagram. Look, lots of dots. It's just a different way of listing them all, but rather than having to write down 1, 1, 1, 2, 1, 3, we just put a dot there. It gives us something we can count. So total 3, well there's 2 of them out of 36, 1 in 18, total 7, all the ones there, 6 out of 36, 1 in 6. Probability at least 3. At least 3, it's probably going to be quicker going 1 minus the complementary, because there's less to count. So 1 or 2, and there's actually only one number. There it is, 1. 35 out of 36. Diagram, tree diagrams, probably one of the more common ways to do it. Raffle, 30 tickets, 2 prizes. Probability, someone buying 5 tickets wins a prize. So we branch out, they could win or lose on the first draw. Then if they win, that changes the probability, so it's now 4 and 29. So if it's not equally likely, we tend to write the probabilities on the branches. If it's equally likely, we don't have to worry about that because we can just simply count. And so there's all my outcomes. I could win, 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 loss, loss, win, or loss, loss. And I worked out all the probabilities. Possibly I didn't have to work them all out for this one. But we want win, loss, or loss, win. 25 on 87. Remember, the probability, if you find yourself saying or, then you're going to be adding the probabilities. If you find yourself saying and, you're going to be multiplying the probabilities. Like here, it's win and win, so I multiplied the probabilities. Whereas over here, it was win-loss or loss-win, so I added the probabilities. At least 1, again let's use the complementary event idea, 1 minus no prizes, 9 on 29. Alright, last year's HSC. In a game, the probability a particular player scores a goal is 0.15. What's the probability that they do not score a goal in the first 2 attempts? So it's actually the complementary. Well here, they told me scoring a goal is 0.15, therefore not scoring a goal must be 0.85, 1 minus. Multiply, because it's not score a goal and not score a goal, 0.7255. Determine the least number of attempts this player must make so that the probability of scoring at least 1 goal is greater than 0.8. We're saying the probability that greater than or equal to 1 goal is 0.8. I'm going to do it this way. 1 minus the probability of just not scoring a goal, because that's now only one thing I have to consider. Greater than or equal to 1 goal would be very hard because I don't know how many times they're trying to score a goal. Whereas this one I'm just saying, look, I still don't know how many, but I do know they're going to miss every single time. That's easier to work out. Rearrange that. Probability of no goals, less than 0.2. But each one of those, because I'm saying not score a goal and not score a goal and not score a goal and not, I'm just multiplying n times, because that's the number of times I'm trying to score a goal. Log both sides, because we want to get that n out of the power. Bring it to the front, remembering of course the log of a number that's smaller than 1 is a negative number. So when I divide, I've actually changed the sign. Change the sign. Change the sign. Becomes greater than. Greater than 9.903079705. Therefore 10. That's how many attempts at goal I need. That'll do us.